Hello again. We are continuing now with some limit laws. This will allow us to compute limits without having to, use our calculator a whole bunch. These are the first two limit laws, very basic ones. The first one says the limit as x approaches a of x is just a. And the second one, the limit as x approaches a of c, where c is any constant, is just that constant. Okay, so these are just two very basic laws. They should be really obvious if you were to look at a graph. Like if you look at the graph of y equals x, then if you pick any value a, there's this point a comma a as x approaches a, y approaches a. So our function's approaching a. And this one would just be if you have a horizontal line at a height of c, so that's the function f of x equals c. Well, then no matter what value of a you're thinking of, well, the height of the function is going to c because the height everywhere is c. Anyway, so that's these two laws. The next couple of laws are going to be a little bit more complex, but once I write them down and talk about them, they're all really, they're not as bad as they first seem. Anyway, let's write down those next laws. All right, so here are 6 more limit laws. They're a little bit more complicated than the last ones. Let me talk through them. Okay, so if you have two limits that exist, the limit as x approaches a of f of x L, limit as x approaches a of g of x is equal to m, then if you add or subtract any two functions and you're doing a limit as x approaches a, then you basically just get L plus or minus the m. The second one, limit as x approaches a of a constant times a function, the constant factors out, and then you just get the constant times L. And one thing you notice as you're going through these rules, and let me just mention a couple of minor things. For the one where with division, you don't want m to be 0, otherwise you'd have division by 0. And if you're doing an nth root, you need to make sure you're not doing the nth root of a negative, even root of a negative number. So this limit would only exist if n is either odd, because odd root of any number, positive or negative, exists, so you wouldn't care then. But if n is even, then a couple of little points for this to be true. If n is even, then L has to be greater than or equal to 0, and your function has to be positive on both sides of a. Because if they were negative on both sides of a, you can't square root or take an even root of a negative number. Wouldn't even matter if L was 0, let's say. If you're trying to approach if fx is approaching 0 from negative numbers, the even root of a negative number doesn't exist, and then your limit just wouldn't exist. So there are some minor things you do have to pay attention. But, okay, so this wall of limits, really not as bad as it first looks, because really if you look at them, in each case, it's like you're replacing f of x with L and replacing g of x with m. That's what the two limits are going towards. See, f of x becomes L, that becomes L and m. L over m, L to the n, nth root of L. So it's really just like you're replacing f of x with L and g of x with m. Okay? So, understanding that, it makes it a lot easier to remember these. You can skip these middle steps and just skip to this, last step right here in each of those cases. But you can sort of fill in the blanks by just remembering that, like the nth root of a function, it's really like you do the limit of the inside and then you do the nth root. Anyway, so like I said, this all of these functions or all these limit laws, not really as hard to remember as it first looks, because in each case, f of x is just being replaced with what f of x is going to L, and g of x, when it appears in some of these, is just going towards what its limit goes towards. Okay, so let us talk about a couple of functions using these limit laws. The two functions that I'm about to talk about are polynomial functions and rational functions. Okay, so this is an example of a limit of a polynomial. We're trying to compute the limit as x approaches a. I've just left it as an a of 2x squared plus 6x plus 7. Okay, and let's use our limit laws and see where we go. First of all, we have addition. So by the limit law for addition, you can break this up into the limit as x approaches a of 2x squared plus the limit as x approaches a of the next piece, 6x, plus the limit as x approaches a of 7. So this was by the sum rule for limits. And then by the constant multiple rule, you can factor this constant 2 outside this limit and this 6 outside of that limit. So then you would have 2 times the limit as x approaches a of x squared plus 6 times the limit as x approaches a of x plus the limit as x approaches a of 7. Okay, now we're going to use those very first two limit rules. Well, actually, have to use the power rule here, because when we have a limit as x approaches a, if something raised to a power, basically the power can sort of be factored out of the limit. So you do the limit as x approaches a of x and then square it. I'll leave these other two limits alone and handle those in the very last step. Okay, so now to the very last step. Using the very first two limit rules that I gave you, the limit as x approaches a of x is just going to be a. Limit as x approaches a of x, once again, a. Limit as x approaches a of a constant is that constant. So this is going to go to a and become squared, so you get 2a squared, and then 6 times a plus 7. So we wind up with 2a squared plus 6a plus 7. And we didn't even have to know the value of a. Now, one thing you may notice is that this is just the same thing as this polynomial, and you've replaced all the x's with a's. And in fact, that is the rule for polynomials. So let's state the rule this way. The limit as x approaches a of p of x equals p of a, where p of x is any polynomial function. So any polynomial function, just plug in a, and that's the answer for the limit. So makes polynomials really easy. Okay, now let's look at rational functions. A rational function is a polynomial divided by a polynomial. Okay, so let's look at an example of a rational function. All right, so here is an example of a rational function. And we're going to be doing, once again, just limit towards any point a of x squared minus 7 over x minus 3. So first, I'm going to use the division rule, which states that you do the limit of the top, assuming that it exists, and then divide by the limit of the bottom, assuming that it exists. And then we can take advantage of the fact that, well, this is a limit of a polynomial. And so you can just plug in a. And this is another limit of a polynomial. So you can just plug in a. So we wind up with a squared minus 7 over a minus 3. Now there is one small issue here, is that when we had our rule for division, remember that we had to watch out for division by 0. So if a was the number 3, this would give you division by 0, and therefore the limit laws just break. The limit laws don't give a result. And so this is true if A is not 3. If A is 3, you know, there would be no conclusion, at least right now. We'll probably talk a little bit more on what to do when you have this weird division by 0 case. But for right now, we can see that you've just taken your function r of x and plugged in a's for all the x's. It's sort of like the polynomial rule, that you can say that in general, that if you have any rational function and you call a rational function maybe capital R of x, then the rule is the limit as x approaches a of a rational function r of x is simply equal to r of a as long as you are not dividing by 0. So little teeny clause, little catch you have to watch out for, but essentially rational functions are exactly the same as polynomial functions. In order to evaluate the limit, simply plug in your a, and if you get a number back out in the case of rational functions, you know, you're not dividing by 0, then that's the value for your limit. Okay, so that's going to be it for now. In the next video, we'll be talking about more complicated limits and limit techniques that you have to use on certain limits. That's it for now. Have a good day.